I'm Anders Hejlsberg. I'm a technical fellow here at Microsoft. I'm the chief designer of the C# programming language, and also I've been involved in the inception of .NET, and I've worked on that ever since we started. And for the past probably actually going on 3 years now, we've been working on this thing we call the LINQ project. LINQ stands for Language Integrated Query. And I'm here today to sort of give you an overview of what that's all about, and hopefully a bunch of demos. I only have a few slides, and then we'll just do the rest in code. That's always more fun. The LINQ project is basically about addressing this problem, the impedance mismatch that we have had and continue to have between databases and object-oriented programming languages. I sometimes say that I'm old enough to remember when data was easy, when you programmed in stuff like DBase or index sequential file access or what have you. And back then, and certainly if you look at things like DBase, language and data were very, very close. It was like your database was right there in your programming language, and constructs to access data and query data was completely natural. But then sort of in the name of progress, databases grew up, and SQL was invented, the relational algebra, a whole theoretical foundation was built underneath data that was actually quite different from the theoretical foundations we have under programming languages. And the two worlds sort of started to diverge, and they've kind of been on a fairly divergent pattern ever since. And now we find ourselves, say 20, 30 years later, in this very complicated world that we use to write enterprise applications today. Like any app that people write, I sometimes ask C# programmers, how many of you access data in your applications? And they all look at me like I'm an idiot, and then they all raise their hands. And of course we access data in our applications. And so, upwards of 80-90% of people that write in C# also talk to a database, which means they also probably have to learn a whole different domain-specific programming language called SQL, and the whole underlying theoretical foundation of relational algebra and tables and joins, and of course they all have different data types in the database for no particular good reason, but so everything is incompatible, and then we give them sort of these fairly low-level APIs to tie things together with queries and strings and manual typecasting and connection strings and what have you, and it's just all sort of degenerates into a plumbing exercise rather than a programming exercise. And so what we're trying to do here is say it doesn't have to be that way. We can actually make progress by taking some of the core concepts of databases and adding them to general purpose programming languages. And of course one of the key concepts there is this notion that you can query data. And actually if you look at this notion, it's interesting too that databases have this wonderful capability and a very declarative functional kind of programming for writing queries. Now you could argue that SQL is not a great programming language, and a lot of things could be done, but nonetheless it does actually represent a very right thing in that it brings you to a more abstract level of programming where you're saying less about the how and more about the what. When you write a query, there's lots of flexibility for the query processor to arrange for the most efficient execution given even dynamic tuning and parameters and whatever. But when you write in general purpose programming languages like C# or Java, you're way too low, right? You're writing for loops and if statements and saying move this piece of data from here to there, and there's precious little the infrastructure can do to make that go faster. I mean, we've all seen, exercises of trying to turn traditional programming languages into concurrent programming languages, like with Fortran, for example, where you try to run it on multiple processors, but you're coming at it from the wrong level of abstraction. You're trying to have to figure out, well, what did he really mean, or she really mean, when she wrote this for loop with an if statement that moves this from there and takes this array element and so forth, and it's at the wrong level. Queries are great because they're actually really at the right level. And so so basically, part of the solution here is introducing a higher level of programming, a more declarative, a more say the what, but not the how level of programming. And then finally, one of the things that we're sort of drawing on in LINQ is a lot of the research that has been happening in functional programming languages over the last 20 years or so. And interestingly there too, there's been this whole branch of a new style of programming emerging that hasn't really seen much mainstream use, or it hasn't really seen any mainstream use, to be honest, like stuff like Haskell and ML and whatever still is sort of firmly rooted and only used in academia. But there's lots that we can draw upon from there and where we can sort of like try to not be quite as purist about the functionalness, but adding functional constructs to an imperative programming language like C#, and we can get some great gains from that. And so hopefully I'll be able to show you that too. So that's sort of a long-winded problem statement. The LINQ project starts with this concept of language integrated query. It really is sort of, think of it as we are now growing the fabric of the .NET framework and the .NET Common Language Runtime. We are growing it with the inherent capabilities of queries, set operations, and transformations. Just like objects and classes are first class in .NET, so are we now making queries, set operations, and transformations completely first class in the platform. And you should really think of this as we want queries to be as natural as for loops and if statements. It's just something that's there. It's something that you can apply to any piece of data that you have, not just some data stored in a database, but an array of customers you have in memory or an XML document that you just read from a web service. You ought to be able to query that as naturally as you would data in a database. So embodied in this language integrated query is a bunch of conventions about how .NET deals with set operations and so forth. Then there are some extensions to our mainline programming languages, C#, 3.0, VB 9.0, effectively grow up now to become full-fledged query languages with the expressive power equal to SQL or XQuery. And there's a complete extensibility story that allows other languages to incorporate these same extensions. And then in the same project, alongside with the language extensions, we are building effectively a multitude of APIs. And I don't even have all of them on this slide. It is an older slide. But we are building an API called LINQ to Objects, or we used to call it the standard query operators. And this is effectively an API that captures a relationally complete query language as an API that you can use. And then LINQ to SQL gives us the same API, but against SQL databases, and LINQ to XML enables the same API to work against XML. And with that said, I'll just jump in and show you some of this stuff in action. And indeed, the rest of my talk really is just going to be coding here. And I invite you to ask questions too. This is a small audience. That's the good thing about small talks. So I'm going to start with a simple little demo to show you how you can query pretty much any kind of data that you might run across in an application. Indeed, I'm going to write a little app that queries the processes that are running on my machine. So I could, for example, say var query equals, and this I'm writing in C# 3.0 at this point. In fact, what you're seeing on this machine here is I have installed the LINQ technical preview that people can download over the web. It's free. And then I put it on top of Visual Studio 2005. So this is stuff that anyone can download and play with. So I'm going to write from p in process.get processes. So you see up here I've imported system.diagnostics, and in system.diagnostics there's a class called process, and process has a method that returns an array of all of the running processes in the system, and now I'm going to write a query against that. So let's say I want to see all the ones where p.workingSet, and here workingSet is just a property of one of my process objects, where workingSet greater than equal to, say, 4 megabytes. And from that I want to select p.workingSet process name, yep, and p dot working set. There. Now, later in my talk, I'll explain what the hell is this he's writing here and how does that all hang together and integrate into the language. But right now, we'll just look at what it can do, and then we'll look at how it works afterwards. So I think everybody can probably understand what the query does is give me from all the processes where working set is more than 4 megabytes, give me the process name and the working set. And now let's try and display the results. So we'll say for each var item in query, and then we'll say console.writeLine and do a little bit of formatting string magic here. So give me parameter 0 in a field of 25 and parameter 1 in a field of 12, numerically formatted. There, and then let's print out item dot process name, item dot working set. There. Okay, let's try and run this. And here you see a list of all of the processes that are running on my box and their working set, all the ones that are more than 4 megabytes. Of course, they come out in random order, so maybe the next thing we want to do is order them. So we could say order by p dot working set descending. So let's take a look at that. And now we see them all, in descending order. We can see that Visual Studio is a hog. Not surprisingly. But you can see that it's very easy to just write up a query over any piece of data here. And this data, of course, could also have been data in a database and so forth. Indeed, let me try and show you next how you can take a query like this and then combine it with data coming from a database. On this machine, I have SQL Express installed, which is also one of those free downloads that people can grab. And in SQL Express, in fact, I can bring up the Server Explorer here. You see that I have a little database called Process Database that has a process descriptions table, and we can open that and say show the table data. And here we see that we have a table that is keyed by process name and contains a description for what that process is. And that's sitting over in SQL Server. Let's say we now want to join this with the query for the processes that I just wrote so that we get a description for each process as well. So let me try and show you how we can do that. In fact, let me first show you how, and I'm going to use this API we have called LINQ to SQL to import this SQL data as classes, to model it as classes in C# first. So I'm going to grab a little snippet of code I wrote here, just so you don't have to watch me type it, and paste it here. And here, as you see, I have 2 classes declared now. I have a class called process description, which maps the table I have in the database, where I have a process name and description. I've just put CLR attributes on there to say these represent columns in my database. And then I put an attribute on that says map this onto the process descriptions table in the database. And then I've also created a class that models the database itself, where I've said map this class onto the process database, and then here I have a table of process descriptions. You see how we use generics to get strong typing of the SQL data. So this models the process descriptions table in the database. And now the D-LINQ API, or the LINQ to SQL API, effectively can arrange for instances of these classes to be produced as we talk to the database. And indeed, let's try and just say process database db equals new process database. So let's new up an instance of process database, and process database effectively you can think of it as representing a strongly typed connection to my database now. And now I have all of the extents of the database, like all of the tables directly available as things that appear to be collection or collection proxies, right? So one thing I could just do is I could say for each var d in db.process descriptions, console.writeLine, and then let's do some more format string magic here, 0, comma, minus 20, well, minus 15, 1, comma, item dot, oh sorry, d dot process name and d dot description. Okay, and then let's do console.readLine. There. So now my program first creates a connection to the database, and then it just rips through the process descriptions table and shows what's in it, and then waits for me to type something. And here we see now as objects this data from my database. And here we see my original query. And now let's say we want to join these together so we get a description for each of the processes. That we can do by just modifying our query a bit here. So we're selecting out process name, working set, and now we want to select out description. So we'll add an additional description equals, and then we'll write here from d in db dot process descriptions, where d dot process name equals p dot process name. So effectively join on process name, and from that select d dot description. And then finally say make that into a singleton or give me null if there's nothing. And let's get rid of this part up here. And then finally, let's go down here and modify our console.writeLine to also print that out. So item.description. So let's try and run this. And now you see a join of the two pieces of data. So I've actually written here a correlated subquery that joins in-memory data with data fetched from a database. Now, yeah?
I have a question. That join, does it do a linear search, or is it?
No. And we'll look at how that works. Because you're wondering how did that get to the database and whatever, and it.
How many queries were there?
How many queries were there? There was a query per. Let me show you here. We can actually say db.log equals console.out. So we can ask to please show me the SQL that gets submitted as you're going, and you'll see that multiple queries get submitted here. Now, a lot of these actually, interestingly then, because we have an OR mapping sitting behind it, the OR mapping then will go, oh, but I've already fetched something with that primary key, so the query never actually gets any further than to here, if you follow what I'm saying. So, and I need to get into what are the inner workings of the LINQ to SQL API, but we effectively maintain object identity based on primary key. So as you fetch one of these process description objects, if you then execute a query to fetch with the same ID, we just grab the one we already have in memory. So you only get one query per ID.
It's not actually a join, it's a query.
Okay, fine. We could write it as a join if you like. So I could actually do it differently here. Let's write it as an inner join. And then let's up here say join d in db Okay, so we can try and do it this way instead. And now you see the query that went across here, though, because I'm joining in memory with database, we fetch the data from the database and do the join in memory. Now, and we could spend hours on ways you can arrange this to do it differently. But you see the query that goes across here is just get me process name and descriptions from that table. And I'll talk a little bit more about how joins work. Let me just try and make this guy back to what we had before here. Okay. And let me continue a little bit with the XML integration also. Yeah.
You said multiple times that this is all very tight, but you've only shown us correct programs. Can you show us programs that failed the test system?
Okay. Okay. Let me do that in the next demo I do, because that's exactly one of the things I want to show. So we have as part of the LINQ project, we're building this in-memory API for querying. We're building access to relational databases. We also have an XML API that effectively sort of leverages all of the knowledge that we built with the DOM into a new API that supports language integrated query of XML and functional construction of XML. So you effectively get something that is as expressive as XQuery and has the transformational, not just the query capabilities, but also the transform capabilities of XQuery. The way I'm going to show that just briefly here is, let's say I wanted the result of this query to be projected as XML. In fact, let's say I wanted to project it as RSS 2.0 formatted XML. Let's say this was a web service. You could hit a URL and get a list of processes and descriptions of everything running on this box, right? So I would need to produce some RSS formatted XML document that I could return as a result of that request. So here I actually went to the RSS website and got an example of an RSS document. And now let me just try and edit this down a little bit, since we don't really have a lot of these pieces of information, and since they're optional, we'll just edit it down to something that says RSS with a channel with a title, and then each item has title and description. And I'll just copy this XML to the clipboard. Now, one of the features we support is functional construction of XML. And effectively, functional construction allows you to construct XML in a single expression, if you will. You can construct an entire XML document. And the best way really to show it is to take this code that I just copied to the clipboard and then go edit. And then one of the little features we have is you can paste XML on the clipboard as the code needed to create that XML in C# with the LINQ to XML API. So if I do that, then you see here we get the code that is needed to create the XML that I had on the clipboard. And you can see how it's done in a functional way, where literally I knew up an XML element with the tag name RSS, and then I passed to that constructor an parameter array, so an open-ended number of parameters that specify the content. So I want an attribute and then an element, and within that element I want elements, etc., etc., etc. Now, let's just try to change a little demo here to say console.writeLine of XML and run. And then we'll see here's the XML that I just created. And now I can go and take this XML and I could just tweak it around. So one of the features we support is indeed that you can embed queries. And really let me just show you first how it works. Let's say we want to say the title here should be process descriptions. And then for each item, what we want to do here is we want to now effectively insert an embedded query in the constructor of this XML element. So I want to say from item in query, select new X element item. So for each item in my query, I want to create an X element. And here I want to take item dot process name as the title. And I want to take item dot description, which came out of the database. And then maybe what I want to do, just so you can see that, whoops, all of the data is there. I want to say new X element of working set, and then also item dot working set, like so. There. So let's try and run this. And now you see, I still have my SQL log attached. But here you see now out comes a document that's RSS formatted that actually contains the results of executing my query, with each of the process names and so forth. Now the way this actually works is that the constructor of an XML element allows you to specify a variable number of arguments. And if those arguments are XML attributes or elements, then they become content in the document. But if what you give as an argument is something that implements IEnumerable, then we will just enumerate it at that point. And so really what's happening here is that the constructor of XElement enumerates this query, which causes the query to execute, which causes everything to kick into gear and produce the final XML result. So that's sort of like the power of deferred execution. And I'll talk more about that in the next demo I do.
What was passed in the construction?
So if you... So what you look at here, so the question is, what is the type of this guy here, right? That's really sort of what we're asking. What is this argument that I'm passing in here, this from query? And a query written using language integrated query syntax, the result of that query is simply an IEnumerable. And then the XML constructor just says, well, if what you gave me is neither an XML element, nor an attribute, nor a string that I can make content, but it's something that implements IEnumerable, then I'll enumerate it and then take each of the elements and do the same to them. And so each of the elements then are elements, so they get inserted as child content here. Now they could in turn have been nested queries, and they just sort of, it nests that infinitum. So you can therefore build hierarchically structured XML, if you see what I'm saying, because you can insert queries sort of at every point, if you will.
Is this being pulled greedily, or is it like sort of, is the data actually being generated sort of like this?
The data is being generated as the constructor sucks them up here and makes them child content. Now we actually have a streaming X element also that captures all of this in a lazy fashion, and not until you save that element does it then consume and immediately make it into XML and write it to an XML writer, so you can write these streaming queries of gigabytes of data without ever storing it materialized. Yeah, in fact, all I would have to change is here to say new X streaming element, and that would be the effect. Okay, let me just go back, and I wanted to talk a little bit. Well, whoops. Or just show you sort of a little bit about this LINQ to objects API. Is effectively a relationally complete query language. You saw me use language integrated query syntax to access it, and you only saw me use a few of the top features here, but there's a whole bunch of stuff encapsulated in that API, and we'll try and look at a bit more of it. I used the LINQ to SQL API. Let me just breeze through this, which effectively, think of it as a lightweight object relational mapping that supports language integrated query. That is what the LINQ to SQL API is. And you saw me use the LINQ to XML API, which, again, you can think of it as a modernized XML object model that supports querying and transformation. Yeah.
Is the LINQ to SQL API another name for this?
D-Link.
Or something about entity stores?
Right. So there's a separate project called LINQ to Entities, which I did not have slides on here, that comes at it. It's effectively another language integrated query supporting API that is built around modeling entities. So a higher level sort of modeling of your business logic and a bunch of services around complicated mapping and whatever, but it will also support language integrated query. So. And you'll see as I go through some of the demos here that language integrated query is really sort of completely separate. There's no notion no understanding or burned-in knowledge in the C# language of the APIs that we target with language integrated query. There's a totally separate extensibility story that allows others to build language integrated query.
Okay, so they're complementary, they're not competing.
Well, they are somewhat overlapping, and we're working on finding, less overlap in that area, let's say, but that's work in progress currently. But certainly the LINQ to SQL API is something that we will ship in Visual Studio 2007, or the Orcus release of Visual Studio.
How do you export the type of what you select from it?
Yes. Okay. So let's get to let's get to some of the C# language features, and then that brings about how do you materialize anonymous types and so forth. But let me first talk a little bit about some of what you saw here. So you saw me write a query that looks sort of like this in C# 3.0, and I'm trying to, on a single slide here, summarize all of the extensions that we have in the C# 3.0 language. So one of these extensions is this thing that we call query expressions that allow you to write from, where, select, order by, group by, joins, etc., etc. Query expressions, or a more geeky way a more geeky term is query comprehensions, are really just syntactic sugar. Well, I guess everything in a language is syntactic sugar at some level, but the way query comprehensions are processed by the compiler is that they are immediately at the syntactic level translated into method calls. So whenever I say where or select, well, that just becomes a call to a method called where, or a method called select, where we construct a lambda expression out of the range variable and the expression that you pass in. And this happens at a fairly early stage in compilation before types have been bound. And then thereafter, we just compile this, and now there had better be a method called where that applies and a method called select that applies, or else this won't compile. But you sort of see how the compiler is not really in the business of understanding what this means. It simply knows how to translate these easy to read comprehensions into method calls. So we then have this thing we call local variable type inference, where you can just write var and you will effectively get a local variable whose type is the type of the expression used to initialize it. So it is actually all strongly typed. It is unlike a var in JScript, which just means object, right? We have extension methods, which I'll talk about more, but extension methods effectively allow you to add methods to types that already exist. And it's just a new lookup rule in the compiler. You'll see how that works. We have lambda expressions. We have also very rich type inference that allows you to write all of this stuff without ever explicitly saying a type, and yet we infer the strong type of all of this stuff. We have object initializers that allow you to specify the values of fields and properties of an object in an expression context as you're creating the object. And finally, we have anonymous types that allow you to cons up types on the fly. Yeah? Yes. And that's simply because we're at a waypoint right now where IntelliSense is not fully enabled. It will be in the final product. Yeah?
Why were anonymous types added?
Let's go do the demo, and then I'll talk about why they're there. In fact, let's switch back. Let me open a different project here. And then let's just start here from a blank query, where here I just have an array of customers. In fact, we could go look at what this stuff is. You see in here that I have a class called customer that has just some fields. So it just holds some data, including an array of orders, and orders just hold some more data. So it's a nice little hierarchical data structure, nothing fancy at all. And then I have a method that can just load some sample customers up. And now I'm holding an array of customers. And now I'm going to try and write some queries and then sort of break it down so you can see, all the mechanics of how it actually gets compiled. So my first query is simply going to be, give me all the customers. And then I have an object dumper that I'm going to ask to just dump out the results. So if we run this, you'll just see here's a bunch of customers that I loaded up and their data. Let me now try and write a query from C in customers. Say where c.city equals London. Select c.company name. And let's try and run this. And you see I get the names of the customers in London. Now let me try and break down first how this all gets compiled. The first thing that happens is that the compiler takes this and turns it into var q equals customers dot, and then because there was a where in my query, it makes where c arrow c dot city equals London. And it literally does this by taking the range variable name in the from clause and the expression in the where and making a lambda expression out of it just by inserting the arrow operator in between the two, and then now it's not doing this at a source level, it's obviously syntactic tree transformations, but that's mechanically what happens. And then because there was a select, we turned that into a select CRC.company name. So that's actually the code that runs. So if we run, you see that we get the same results. Okay, so now we need to break down two things here. First, what are these lambda expressions, and where did these methods where and select come from? And what does this var guy mean? So I'll try and break those down. So first of all, a lambda expression is simply a more compact way of writing an inline function. Now these two lambda expressions I wrote here, I could pull them out and make them separate. So I could say function of customer, comma, bool, filter equals lambda expression crc.city equals London. And then I could say function of customer, comma, string selector equals c.company name. And then I could change these guys to just be where filter select selector. So first, there's nothing magic about lambda expressions as such, you know, when they occur in a method call. They can first be assigned to local variables and then passed to the method call. So if you run this, you still see the same results. And what we've done here is we've created two local variables where we're storing the lambda expression c.city equals London and the selector also. Now, again, the way we give type to this, it becomes a little more obvious when we assign it to a local variable, is that we say a lambda expression. So effectively, this part here has no type per se, but it is a construct that is implicitly convertible to a compatible delegate type. So we have sort of, this is what our expression is, and this is the type we're trying to convert it to, which is a function taking customer, returning bool. And when we plug in customer as the type of C and bind this guy, then we do indeed get a valid expression that is convertible to bool, and therefore the conversion succeeds, we say, and therefore we can now create a function with those types and create a delegate to it, and that's the result of the expression here. I could, I could actually sort of go even further and show how this is just simply a separate function that I could create a delegate to. I'm not gonna do that. But the next thing that you're gonna wonder then is, well, first of all, the other thing that happened was that we actually inferred the type arguments here. So we inferred that there's a type argument T here of type customer. Whoops. And we inferred that in the select there are two type arguments, customer, comma, string. So again, type inference has inferred this, and you know, I can compile it with or without those specific annotations. Now, the var guy here effectively just means give me a local variable with the same type as what was on the right-hand side. So this is really the same as saying IEnumerable of string q. And again, you'll see, get the same result. And now the final thing we need to look at is where did these where and select methods come from? Because customer is an array of customers, and if you go look in .NET, you'll note that there is no where method or a select method on an array. These guys are extension methods. They were brought into scope because I imported system.query. And we could go look at the source for system.query. And in system.query, you'll see, well, actually, one of the first methods is a method called where that takes an IEnumerable of T and a predicate, which is a function of T, comma, bool. And the way it's implemented is it's a little iterator that for eaches, and if the predicate returns true, then it yields the elements. The thing that's special about this method is that it's declared with a modifier, this, on the first argument, and that marks it as an extension method. And this method effectively appears to extend IEnumerable of t when this method is in scope. So when I import the namespace system.query, then we will look in all static classes in that namespace and find all extension methods and bring them into scope, so to speak. And the way they then get resolved is that when we do the lookup of where, so we go customers.where, well then we first look on customers. We use our normal lookup rules to see is there a where method. If that lookup fails, then we look in all of the extension methods that are currently in scope after turning the receiver of the call into the first argument. So we map that guy over, and then we look up and see if there's a method that now applies, and that's where we find the extension method where, and that's the one we then bind to. So in fact, when I write this stuff, it is really the same as writing sequence.select of sequence. Well, let me, and this is where it starts getting ugly, and then you can sort of see why we're doing it, but this is the same as saying sequence.where of customer of customers, comma, filter, and then calling sequence.select on that, passing the argument selector there. And if we try and run, oops, turn this into a comma up here, there, and then let's try and run it. And you see we still get the same results. And this is effectively, now we've broken it all the way down to what actually got compiled. Yeah?
Is it possible to print your own sugar, basically, say you want to print your own?
Right. The comprehension syntax is fixed, meaning that you cannot add new comprehension translation rules, and so we don't have expressivity for that in the language. You can, however, add new extension methods yourself. And so really we say the extension, the method whereby we get extensions into this system is by writing new methods, by writing new extension methods. That is our extensibility model. Yeah. Oh, yeah, let's go in the back there.
Is it possible to add another extension method and say IEnumerable and call it the original?
Yes, yes. Now, and the way it breaks down, you can see is that even, let's say there were two methods called where, and that overload resolution could not pick between them. Let's say they had identical argument lists. Well, then you get an error, an ambiguity error. But you can always call them just like static methods. And here you are actually saying that, oh, I meant the static one in the class sequence, if you see what I'm saying. So you can always disambiguate simply by using regular method calls. But obviously, you can see, I mean, the thing that's interesting is that you look at this and you go, what the hell is this, right? I mean, this is like so unappealing syntactically, but it's all just sugar, right? But you put it together in the right way where things are strung together, dot, with type inference, so you never have to say the types, and all of a sudden out of this fog appears, a query language. The thing that's interesting to note here too is that the one last thing maybe that I should just talk about is, let me try and take this back to the query that we had a little while ago that says var q equals customers dot where city London, select the company name. The one thing that you perhaps can't see from this is, but nonetheless is a super important thing, is that execution in this system is deferred. Deferred as long as we possibly can, effectively. So the statement var q blah, 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 blah executes immediately. And the where method, all it does is it allocates a little object, it's like a 16-byte object, that holds on to the source and holds on to the delegate. And it itself implements IEnumerable. And then the select guy holds on to that source and the delegate to the extraction function. So I've just built a little graph of objects here that are holding on to each other. And then when I for each on it, then that's when the query actually executes as a pipeline, sucking things, the selector sucks from the where guy, sucks from the ultimate source. The where guy drops all of the ones that don't meet the filter. The select guy transforms them and then yields them out. So execution is deferred and is amortized for a number of the operators, like the where and select operators. If I was sucking on 1 billion records and I stopped after 10, because I'm for eaching, and I break after I've seen 10, then work stops. We don't produce the rest. Now that obviously can't be true for all operators, like order by and group by. You got to have all of them before you can do the work. But for a lot of them, you can truly amortize. Yeah. Yeah.
But you actually want to change later that implementation where, since they're static methods, that compilation.
Yes. Well, so that gets us to the next thing I want to talk about, which is expression trees and how we get this translated into SQL. I think it gets us to it. So let me see if that answers it. Yeah. What? Oh, repeat the question. The question was whether you can substitute later the implementation of where. And I think this starts to touch on expression trees and whatever, which I'll talk about in a little bit. Yeah.
So how does this work as far as compiler diagnostics messages? Do you have leakiness from the underlying abstraction?
Well, you sort of have a little bit of leakage of abstraction in the sense that let's say I set a breakpoint here. Yeah. Let's see. Okay, now I want to set debug toggle breakpoint. Okay, well, let's set a breakpoint on the whole guy. So I know I can set a breakpoint on just the lambda, but it may be that. Anyway, what ends up happening, you can set a breakpoint in the lambda, and what happens is that, well, let's just see. If I put it on a separate line, then I think I might have more luck. Let's try and set a breakpoint here. No, it still wants to break on the whole thing. I don't know why that is. Yeah, I could step into it. So let's try and set a breakpoint here. Okay, and then let's just try and run with the debugger. And you see we hit this breakpoint. And now let's try to step into. Okay, now we're in the object dumper. Okay, now of course. May not be where we want to. Oh, yep. And now you see we step into c.city equals London. So now we're evaluating this predicate for one of the customers that we're sucking out of the enumerable. So it may be surprising in the sense that this code, these lambda expressions don't execute where you might initially intuitively think they do. But on the other hand, if it wasn't for this, I think the whole system just would never work. Okay, now we step back. So anyway, let's just try and run this guy to the end. Let me talk a little bit about what the sort of profound importance of this deferred execution. What happens is that because execution is deferred and because we don't produce any of the results, like indeed if I were to say this first, let's say start with this. Var q1 equals this, and then say var q2 equals q1 dot select there, and then dump q2. You'll see I get exactly the same results. And indeed, if you looked at the code, it would be the identical code too. So composition in this system is effectively free. And because composition is free, we can break the relational algebra down to its constituent components like filtering, projection, ordering, grouping, And once we break that all down and we have a method for stringing them together, then we have lambda expressions, then we can actually make a query language out of an API by composition and passing code as parameters. And type inference makes it such that we don't have to state the explicit types everywhere, and this is what gets us now into why anonymous types are important, and I'll get to that. But there's a lot to cover there. Yeah?
I have a two-part architecture question. Like you mentioned before that the query run and then the filtering is done in memory.
Uh-huh.
Now, what if, for
Right. So we're getting there. We're getting there. Yeah. So let me just talk a little bit about anonymous types, and then we'll look at. So if I say var q equals from C in. So before I was selecting C.company name. Now let's say I wanted the name and the phone of this guy. In C# or in most sort of typical object-oriented programming languages, we don't have the notion of projection as a first-class citizen. SQL has it as a first-class citizen. You just select company name and phone and and a type is sort of cooked up on the fly that structurally represents that, because SQL effectively has structural typing, right? We have nominal typing in C#, and so the question is, how do we get a projection out of something like this? How do I say I want the company name and the phone? Well, sort of the object-oriented C# way would be to go write a class called contact with a company name and phone property, and then in my select here I could say new of a contact and pass to its constructor company name comma phone, and now I would have transformed my customers into a sequence of contacts, so to speak. But now, of course, I have to go write a contact class and add properties to that, and it sort of degenerates into a bunch of writing that I don't care to do. So for that reason, we support what we call anonymous types. So I can just write this, and I'll talk about what that does then. Oops, not Q2. Yep, just a sec. Let me run it, and then you see that I get a sequence of something that has a company name and a phone property. Now, what actually happened here was that the compiler used type inference to infer what the types of these two properties are supposed to be. And since I wrote it here, I'm not just projecting value. I could have written it this way: name equals and ph equals. And now I have changed the names of the fields. But I can effectively abbreviate this even further down to just company name and phone. And then we project not just the value, but also the name of the member. So the compiler cooks up a class that has two properties, company name and phone. And then it returns an IEnumerable of that type. And of course, we would be in a bind now if if we had to declare a local variable and we didn't have local variable type inference, because we can't say the name of this type. But local variable type inference comes to the rescue and allows us to capture that type in a local variable without having to say its name. So now we're holding actually a strongly typed IEnumerable of mumble that has company name and phone. Now, just to sort of prove that it's strongly typed, I could then say for each var item in Q console.writeLine, and if I say item.company name, let's try and run this, you'll see that works. Now if I try to pick something that isn't there and I try to run, you'll see that I get a compile time error. There is no company name XXX. So the type has actually flowed out of the query through this local variable and into the for each, and now I'm decomposing, and again through type inference the type of each item becomes that type, and now I get a compile time error because it doesn't have that property. So even though this looks like a dynamic programming language because I never set a type anywhere, the types are actually present. And you get all of the benefits of strong typing here. Indeed, you know, once we do finish the product, when I press dot here, you will see a drop down, and that drop down will show you company name and phone, so you will get IntelliSense and all of these productivity features that we've all gotten accustomed to.
Since I'm not a completionist, since I'm using the attributes of what's returned, I'm still kind of bound to that data contract.
Right.
So in a sense, I have to know already what the type is. So what is the advantage of having that var there instead of just using an interface for that data contract?
Right.
And letting the environment instantiate it like a proxy, an implementation.
Sure. No, you could do that, but it would be more.
What is the question?
Okay, sorry. The question is, what is the advantage of anonymous types? I could have just maybe written an interface with these properties and then having the environment instantiate that interface, and sure, you could, but it would have been more typing, right? I mean, the point is here that if you want composition of queries, if you want to break a query down to its constituent parts, like let me first say do this inner join, and then I'm going to do in that consume that in an outer join, and da. You need a way of representing the result of that query so you can consume it in the next and so forth to compose things together, right? If we forced you to create a nominal type at every juncture, it would be a royal pain to work with this system, right? So you need a way of just completely seamlessly allowing the types to flow. Now, of course, once this type gets into a public contract that you want to share with someone else in another application, anonymous types aren't going to cut it for you anymore. Indeed, we naturally limit anonymous types to the method that you are within, because there's no way of capturing the anonymous type. I couldn't say this function returns var, nor could I have an argument of type var, so you must make them nominal at that point. Now, we actually plan to have a refactoring that allows you to just click here and say, give me a nominal type, please. And since we have strong typing, we know everything. We can just poof, pop a class into existence with those properties and change this new here to be new contact after you've told us to call it contact, and then you're in business. So in terms of typing, it's not going to be very painful to do this. And because we have all the strong information, we can actually do it through refactorings and you write it this way, and then you say, okay, now I'm going to share this with someone else. Give me a type here. And we can just pop the type out for you automatically. I mean, we can write the source code and literally put it in your source file, right?
You're using the application metadata for reduced to physical source.
Yeah, you could say, yeah. I mean, before I write the type, yeah. Okay, so since I'm almost out of time and I still need to talk about expression trees, let me show you now how we get to an efficient implementation of an object relational mapping on top of this stuff. Now, let's say that what I was querying here was, well, in fact, let's change it a little bit and say import north wind here, and then let's change this instead to be okay, so slight change to my program. So right now I'm importing the Northwind namespace. If we go to look in my solution here, northwind.cs, I have run a tool and pointed it at against a database called Northwind. And if you've ever done any programming on the Microsoft platform, you know the Northwind database. It's just a little simple database with customers and orders and details and products and suppliers and so forth. And we have a tool that you can run. You can just point it at the database and say, extract me an OR mapping for this database. And that's what I've done here. And it effectively gives me a strongly typed object-oriented representation of the database. So I now have my Northwind database with an orders table, products, order details, If I go look at one of these guys, you'll see that for each of these tables, let me go to the product class, we generate a class, and the class we map to a table, and we generate instance variables and properties that map to the corresponding columns in the database. And now I can effectively work with my database in an object-oriented fashion. And I'll talk about now how do we then make queries against this database, run in the database instead of running locally, which would be very inefficient, right? So if we first sort of observe that it works here, so I'm creating a Northwind connection to my Northwind database, and then I'm querying db.customers. And if I run now, well, you'll see effectively the same results. Maybe I should just try to attach here db.log equals console.out. And now you can see that I get the same results, but this time the data is coming from a database, and the query that got executed was select company name and phone from customers where t.city equals blah. So you see that we actually have taken this code that I wrote in C# and somehow magically turned it into SQL. And we have understood what columns you projected out and what the predicate expression was and so forth. Now let me talk about how that happened. Again, the rewrite that happens is exactly the same as before. So we say C arrow C.city equals London. And then we say select C arrow new blah blah blah. Now, this in turn then means that we will call the where method and the select method of customers, of whatever customers is. So if we go into the Northwind guy here and try to follow what is customers, you'll see that we have a table of customer. And that's actually what we're querying here. Now, table of customer implements a method called where and select and order by and group by and blah, 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 blah. But instead of asking for a lambda expression here, that where method asks for an expression tree. And the way it does that is we could write something like func of customer comma bool c equal or f equals c arrow c.city equals London. So if I write this first, then I get myself some function that takes a c and returns c.city equals London. And we can turn this into IL and to a delegate that points to that IL, and then you can invoke f and it'll tell you whether the customer has a city equals London. In fact, maybe we should try and just do it with simple little stuff. Say function taking int returning int f equals x arrow x plus 1. And then let's just try and say console.writeLine of f of 5. Get rid of this stuff here. And let's try and run this. And then you'll see that I get the value 6 out of my lambda expression here. What we permit you to do, though, is to say expression. So we have a class called expression that takes a lambda as a t, or sorry, takes a delegate type as a t. And this now will instead create an expression tree, a strongly typed expression tree. So an expression tree representing a lambda taking an int, returning an int. Now, if I were to console.writeLine f itself now, you will see that we've actually captured a tree. This is the toString of the expression node, and the toString of the expression node walks the tree and shows you the nodes that are in there. So there's a lambda node that takes an add node that takes an x and a constant 1, etc., etc. And really, lambda expressions now just become literal syntax for newing up expression trees. And what the compiler does is it actually targets a new API called system.query.expressions, which is an expression tree object model that's built into our class library. And lambda expressions become a way of just conveniently newing up expression trees in a strongly typed fashion. But you could have newed it up yourself. So you could literally new up an add node with a param node with a blah, blah, blah. And of course, it's very gunky and low level. But the point is that you saw that I can now, in my methods, ask either for lambda expressions that are directly callable or for expression trees that represent what the user wrote in the lambda expression. And that's what we do in order to turn this into SQL. We ask for trees, and then we build up a whole tree representing the query. And then when you for each on it, when you enumerate, that's when we can look at everything, turn it into SQL, submit it to the database, and then create objects on the reader that comes back, if you see what I'm saying. Just the final thing let me show here is that we actually have a service that allows you to compile expression trees and produce the actual lambda. So if I say this is my tree, E, then I could indeed say bar f equals e.compile. And this actually type inference here, this is the same as saying func of income int f equals compile my tree. And now if I invoke f of 5, you'll see that, whoops, console.writeLine f of 5. There. You'll see that I get the result 6. And what happened here is that we take this tree that you could have dynamically created, and we compile it to IL using reflection emit. and now you're just invoking IL here. So we actually have, sort of a whole meta programming system captured in an API, and then the language fanning into it by giving you lambda expressions that allow you to write expression trees. So anyway, and now I'm out of time. I'm over time. So I'll take. You can also talk to stored procedures. I don't have time to show it here, but we import stored procedures and allow you to make them look like CLR methods.
What happens if you call a method that is not that cannot be translated into SQL?
If you call a method that can't be translated into SQL, then we'll give you an error. But there are some fairly intuitive rules for what can be called and not called, and so yeah. Last question, and then I'm going to wrap up.
I noticed on one of your early examples you had an equals keyword, but I'm wondering
Yeah.
if you have the expression for deferred execution, why you couldn't use equals.
Okay. This has to do with how we translate the join. Okay, why did we have an equals keyword as opposed to an equals operator in the join syntax? And it's an involved, there's a good reason, but it really has to do with how we do the comprehension translation and how it would be surprising if we used equals, because people would think you could use greater than equals there, and you can't, because a join is only an equijoin. And so anyway, okay, well, I'm sorry that I ran out of time here, but there's so much to cover and so little time. So thanks for listening, and feel free to send me email andersh@microsoft.com if you have additional questions. Thank you.